Good morning to Sir Hanif and my friends. Today I'm going to present about my case study presentation, which is vehicle dynamic analysis of Proton X50 1.5 TGDiFlagship 2023 model. My name is MOHAMAD HAIQAL bin HERMAN. Okay, for the introduction, vehicle dynamics is the study of how force and moments affect a vehicle's movement. This knowledge helps engineers design cars that are safe, comfortable, and perform well. This report focuses on applying the theory of vehicle dynamics to the 2023 Proton X50 1.5 TGDiFlagship through engineering analysis. The main goal is to study the force acting on the vehicle during different driving conditions. This includes calculating load transfer, checking powertrain performance in several gears, and analyzing ride steering and tire behavior. The study is based on the Proton X50 official specification and will cover topics such as axle loads during acceleration on a slope, traction limits, aerodynamic improvement, suspension performance, and steering geometry. In the end, the report will give database suggestion for improving the Proton X50 overall performance and handling. We are going to the next slide. This is 7 objectives. For the first one is to examine the dynamic behavior of the Proton X50 during acceleration, braking, and cornering. The second is to calculate the static and dynamic axle load distribution, including load transfer during acceleration on an inclined surface. The third one is to evaluate the powertrain performance by determining tractive force and traction limits in the first 4 years. Number 4, to determine the suspension ride rates and natural frequencies to assess ride comfort and vehicle stability. Then number 5 is to apply a command steering geometry in order to calculate steering angles and evaluate steering performance. The number 6 is to analyze the tire specification and their influence on traction, handling, and overall vehicle dynamics. For the last one is to propose aerodynamic and mechanical design enhancement that can improve the Proton X50 performance, safety, and comfortable. This is the scope of the case study. We have 7 scopes. Okay, for the first one that we can see analysis of the Proton X50 performance during acceleration, braking, and cornering. The second one is determination of static and dynamic axle load distribution, including effect of incline. Calculation of tractive force and traction limits across the first 4 transmission gears. Number 4, evaluations of suspension ride rates, tire stiffness, and natural frequencies to assess comfort and stability. Number 5 is application of HERMAN geometry to determine steering angles and turning behavior. Review of tire specification and their contribution to overall handling and safety. For the last one is proposal of aerodynamic and design improvement to enhance vehicle performance. This is our vehicle data analysis. We have the first point is vehicle data weight and dimension that we can see. We have a 1,355 kilogram for the crop weight. For the vehicle gross weight is 1750 kilogram. For the wheelbase is we have the 2600 mm, which means like 2.6 meter. We have a track width, we have the overall length, overall width, overall height. We have the assumed center of gravity is CG, height is H, and estimate static distribution. For the second point is we have the transmission gear ratio data. With the transmission 7-speed with dual clutch transmission, which is DCT. Final drive ratio, and we have a gear ratio: first gear, second gear, third gear, 5 gear, 6 gear, 7 gear. We have a peak torque which is 255 Nm, and we have a estimated drive strength efficiency. Next one, we have the tire and suspension stiffness data that we can see a lot of data right here. Tire size 215 stroke 55 R18. Then we have a calculate tire radius. We have a radius and saturation type. Next, vehicle turning radius data. Turning radius for this vehicle is curb to curb 5.4 meters. And then we have a tire and name details like tire brand and model. We use a Goodyear Eagle F1 asymmetric 3 common fitment. And then we have a tire size 215 stroke 55 space R18. We have a speed and load rating 93 volt. Max load is 650 kilogram per tire. Max speed is 240 km per hour. And we have a rim size 18-inch alloy wheels, and rim width 7J 7-inch. Offset ET is ET55.
Okay, let's move to the next part. So the first question is the axle load distribution. For the axle load distribution, it refers to how the total vehicle weight is divided between the front and rear axles. The axle load distribution affects the vehicle's stability, traction, braking, and handling. The static axle load distribution describes weight distribution when the vehicle is stationary, and it depends on the center of gravity position and wheelbase length. And it also determines how much load each axle supports under normal conditions. So for our first questions, from the vehicle data, we get that the mass of the car is 1,355 kilogram. Then the weight is 13292.55 Newton, and the angle is 4%, and the acceleration is 3.7 meter per square. And the center of gravity is 0.5 meter, and the length of the car is 2.6 meter. For the weight distribution of the car, so for the front is 61%, for the rear is 39%. So the first step is we need to find the front weight of the car. So we put the 13292.55 Newton times to the 61%. So we got the front weight is 8108.46 Newton. For the weight of the rear, we take the 13292.55 times by the 39%. So for the rear weight of the car, we get 5184.09 Newton. So we find the WF. So the formula for WF is W times LR per L. So for the answer, we get that LR is 1.59 meter, and for LF we also get the answer is 1.01 meter. Next, let's find the angle of the car. First, we use the formula tan theta equals to 0.04. So the theta equals to 2.291 degree. So after we get all the data such as the LF and LR and H, we have H. Now we need to find the real WF and WR. So for the WF, we use the formula W times LR cos theta minus H per G times AX minus H sin theta per L. So for the WF, we get the answer 7056.09 Newton. For the WR, the formula is W times H per G AX plus H sin theta plus LF cos theta. So for the WR, we get the answer is 6225.84 N Newton. So we finally get our final answer for the axial load distribution for front and rear. So the dynamic axial load transfer occurs during acceleration or braking. When accelerating, weight shifts to the rear axle. When braking, the weight shifts to the front axle. It influenced by the height of the center of gravity and the vehicle's acceleration. So the purpose in the study is to understand how the Proton X50 maintains traction and balance in different driving conditions. It also helps in analyzing tractive and braking force. And it also useful for evaluating suspension performance and vehicle handling. So let's move to question number 2. Tractive force and acceleration. So the A is we need to find the first until the fourth gear tractive force. So for the gear tractive force is the driving force transmitted from the engine through the tires to move the vehicle. It determines how effectively the vehicle can accelerate, climb hills, and overcome resistance. So the purpose is to evaluate the powertrain performance of the Proton X50 in each gear. And it also helps identify which gear provides the maximum traction and acceleration. That it is important for analyzing traction limits and vehicle drivability. Number 2. Factors affecting tractive force. First is engine torque, power produced by the engine. Next is gear ratio, determines torque multiplication at each gear. Next is final drive ratio, further multiplies torque before reaching the wheels. And the last one is tire radius. It converts torque into linear force at the road surface. In the study, the tractive force for the first 4 gears will be calculated using the vehicle torque and gear ratios. Comparison across gears show how force decrease as speed increase. Results help assess the balance between performance, traction, and fuel efficiency. So, for the question A, the question asks us to find the first until fourth gear tractive force. So, from the vehicle data, we have the ratio of the first gear until the fourth gear, the final gear ratio, the TE, the NM, and the radius of the wheel. So, to find the gear ratio, the formula that we use is F equal to TE times NTF times NTF and times NF per R. So the answer for our first gear tractive force is 9685.11 Newton. For our second gear tractive force, we have the answer is 5952.22 Newton. For the third gear tractive force, the answer is 4211.9 Newton. And finally, for the fourth gear, the tractive force is 3446.62 Newton. So next, let's move to the traction limited acceleration if the coefficient of friction is 0.62. Traction limited acceleration refers to the maximum acceleration a vehicle can achieve before the tires start to slip. It depends on the tire rod friction and the weight on the driver wheels. The coefficient of friction, which is 0.62, represents the available grip between the tires and the rod. When the tractive force exceeds this grip, the tires lose traction and spin. These condition limits show how fast the vehicle can accelerate safely. So, the purpose of the study is used to determine the maximum possible acceleration for the Proton X50 without wheel slip, and it helps analyze how tire grip affects performance on different road conditions. And the last one is important for assessing vehicle stability, traction, and safety during acceleration. So, the question B asks us to find the traction limited acceleration if the coefficient of friction is 0.62. So, from the data we have, the vehicle data, we know the weight of the car is 13,292.55 Newton. And the coefficient of friction is given, that is 0.62. The wheelbase of the car is 2.6 meter. The head of the car is 0.5 meter. So, for the first step, we need to find the WFS. The WFS is given, it is 7056.09 Newton. So the first step is we need to find the mass of the car. So we use the formula W equals to mg. So the mass we get is 1355 kilogram. So to find the Fx, we use the formula the coefficient times WFS per 1 minus H per L and the coefficient again. So for the Fx we get 3908.73 Newton. After we find the Fx, to find the Ax, we use the formula Fx equal to MAx. So we will get the answer for the Ax is 2.88 meter per second cube. Meter per second square.
Okay, next let's talk about aerodynamics and fuel economy. The modification to reduce aerodynamic drag and improve fuel economy. 1. Body shape improvement. Design a smoother and more rounded body so air can flow easily. Lower the ride height to reduce area exposed to the wind. Use a sloping roofline or tapered rear end to reduce air turbulence at the back. 2. Aerodynamic add-ons. Add front air dams or spoilers to guide air around the car instead of under it. Next, install a rear diffuser to smooth the air leaving the vehicle. Use underbody covers to reduce turbulence under the car. Fit wheel covers to low drag rims to lessen drag from spinning wheels. Number 3, surface and component design. Use smaller or streamlined side mirrors to reduce air resistance. Install flush mounted windows and headlights to avoid air catching on edges. Seal panel gaps so air doesn't enter and create drag. Number 4, engine and cooling adjustment. Add active grill to shutters to control airflow into the engine bay when cooling isn't needed. Optimize vents to direct air smoothly and reduce turbulence. 5. Overall effect. These changes help lower the drag coefficient and frontal area, resulting in better fuel economy, especially at higher speed. Next, suspension and ride rate analysis. As you can see, the front rear axle ride rate. Ride rate measures the stiffness of suspension on each axle. It determines how much the vehicle springs compress when a load is applied. A higher ride rate equals to stiffer suspension. It means less body roll but firmer ride. Then a lower ride rate equal to softer suspension. It gives you smoother ride but more body movement. Purpose in the study is to evaluate the suspension performance of the Proton X50, helps understand ride comfort and vehicle stability, used to calculate natural frequency of the suspension system, important for balancing comfort versus handling for front and rear axle. Next is front and rear axle natural frequency, hertz. Natural frequency is the rate at which suspension oscillates when disturbed. Measured in hertz, it shows how quickly the vehicle reacts to bumps or road irregularities. Higher natural frequency give you stiffer suspension, give you quicker response, less body movement but a harsher ride. Lower natural frequency give you softer suspension, give you smoother ride but more body motion. The purpose of this study is to assess ride comfort and stability of the Proton X50. Helps balance handling performance and passenger comfort. Calculate separately for front and rear axle based on axle rates and sprung mass. Useful for suspension and tuning, evaluating how the vehicle reacts to the two different loads or road condition.
HAIQAL steering geometry. Ensure that all wheels turn correctly during cornering. Have the inside and outside wheel follow different turning radius without tires curving. Reduce tire wear and improve steering efficiency. And lastly, it's important for vehicle stability and handling when turning. Purpose in study: to determine steering angle for the Proton X50 during turn. Ensure smooth cornering and proper alignment of front wheel. And lastly, help evaluate how steering design affect maneuverability and tire performance.
I'm gonna talk about advantages and disadvantages of tire changes. The advantages for changing to wider or lower profile tires is it improves grip and cornering. Larger contact patch increase traction during acceleration, braking and cornering. Next, it's gonna enhance steering response. Stiffer sidewalls reduce flex, giving more precise steering. Next is aesthetic appeal. It fills wheel arch for a sportier look. The advantages for changing tire type is for versatility. All season tire perform well in dry, wet and light snow condition. Next is for longer tread life. Harder rubber compounds wear slower than performance summer tires. The advantages for changing to a different tread pattern for superior water evacuation. V-shaped channels water away, reducing hydroplaning risk. Next is to improve and cornering. Larger contact patch improve traction. Next is enhanced steering response. Stiffer sidewalls improve turn-in feel. Next is for aesthetic appeal. Tires with sporty tread patterns enhance vehicle appearance. The next is disadvantages. The disadvantages for changing to wider or lower profile tires is increased rolling resistance and reduced fuel economy. Larger contact patch increase friction. Next is harsher ride quality. Shorter sidewalls provide less cushioning. Next is higher cost. Larger wheels and low profile tires are more expensive. The last one is risk of wheel damage. Less sidewall protection makes rims more vulnerable. Next, disadvantages for changing tire type is compromised performance. All season tires don't match the grip of summer tires or traction of winter tires. The disadvantages for changing to a different tread pattern. The limited rotation option can only rotate front to rear on the same side, which may cause uneven wear if not managed. So the conclusion is, this case study helped me understand how vehicle dynamics affect performance of the Proton X50 1.5 TGDi flagship. From the calculation, I learned how to load distribution, traction and gear ratios influence the car movement, especially during acceleration and uphill driving. The study also showed how suspension stiffness and tire selection affect comfort and handling. Besides that, aerodynamic improvements such as smoother body design and better airflow can help reduce drag and improve fuel efficiency. Overall, this project showed that good vehicle performance depends on balancing power, handling, comfort and efficiency. So that's all for me. Thank you.